Hi. In this lecture, we'll be doing a very simple review of one of the papers that we published recently in Archive. And this paper was about using scientific machine learning approach for predicting the degradation of battery, especially for electric vehicles. So before going into the review of this paper, I would like to give a shout out to Sharv Murgai. Sharv is actually a high school student. So he spearheaded this effort along with Rishikesh Bhagavat. So really hats off to both of them for putting this work together. And of course, along with Raj Rajat and myself, we worked on this paper together for several months, and it's been published in Archive. And Sharv also got selected to present a smaller portion of this work at an earlier stage at a prestigious conference called MIT URDC. And this was actually in the second week of October. So Sharv went to MIT and presented the work. So it was a very satisfying experience for us to formulate this problem as a scientific machine learning framework. So the idea is that electric vehicle batteries, lithium-ion batteries, they degrade. And they degrade in two ways. One is called calendar degradation. This is basically the degradation of battery simply because of time. You don't have to do anything. If you just keep the battery aside, just with time, the battery keeps degrading, the material will keep degrading. And when we say degradation, what we simply mean is the capacity of the battery. And you must have seen this even when you purchase some electronics item, let's say a tablet or a mobile phone. Even if you don't use it, I have a Samsung tablet which I have barely used, and its battery capacity has significantly degraded over the last, I would say, 3 to 4 years. The second type of degradation is called cycle degradation. And as the name suggests, this degradation occurs because of the cyclical usage, charge-discharge cycle. So cycle degradation is based on frequency of usage, and discharge and current calendar degradation is simply because of time. Now you can imagine, like, there are possibilities for accelerated experimental studies where you can charge and discharge battery faster to kind of simulate the cycle degradation. So instead of waiting for the degradation to naturally happen as a result of usage, which actually happens over many years, not over few hours or few months. So usually if you look at the state of health, which is the charge capacity, it degrades from, let's say, close to 100% to maybe 80 or 70%. And this happens over 5 to 10 years. So how do you really simulate this in a lab if you want to study this rate of degradation, everything? You can perform accelerated studies, but it is more possible for cycle degradation than for calendar degradation, because calendar degradation happens naturally. So what we wanted to study was, is it possible for us to make a prediction of the state of health of battery as a function of time? So this is time axis. This is state of health as percentage. So what we were trying to answer was the question of, can the SOH or state of health be predicted given some information about the battery plus some experimental data or numerically simulated data, which will serve as the ground truth. So that was the idea behind our study. So let's go into the paper a little bit. As you all know, like, ever since the boom of Tesla happened and the electric vehicle market cap crossed, probably, I don't know, I think the market cap is easily more than $1 trillion, because Tesla itself has a market cap of $800 billion or something like that. It was 1 trillion at some point. I'm sure the total EV market cap is much bigger than that. And the main component that drives all of this is lithium-ion batteries. And there are companies that are trying to build batteries that are using alternate sources, but lithium-ion batteries are the most common ones. And lithium is it's a rare commodity. It's not available that much on Earth, so it's finite. So either we have to figure out ways to prolong the life of lithium-ion batteries, or we have to figure out ways to make batteries that are as efficient as lithium ion, but without using lithium. So, but we are going with the first approach where we will assume that lithium ion batteries will be used for very, very long time to come. And the only thing that makes sense for us to do is figuring out how to prolong the life of the battery, how to estimate when the battery is going to die, by how much, and creating good, accurate models that can predict the health of battery, so that we can make use of the battery and we can make use of its life cycle in the most efficient way. So that's the idea behind this paper. So I don't want to go into the exact chemistry behind the battery degradation. That I will let you go through the paper. I'll share the link in the description. But I just want you to have a look at the calendar degradation. So this is the calendar degradation equation, in which there are a few terms. So it's integrated the Q calendar. This is integrated over 0 to t, and it depends on time, of course, as you can imagine. It depends on temperature. It depends on activation energy, and there is a universal gas constant. And one term which you might not be familiar is this SOC. It's a function of SOC. SOC means state of charge. So the value of this parameter, so this is more like an empirical parameter, where you can estimate based on state of charge what is the value of this function. And so this is like a piecewise function. So you can imagine, if the state of charge is, let's say there are three ranges of state of charge, right? If state of charge less than 50, if it is between 50 to 70 and 70 to 100%. So it's like a piecewise function. So between 0 to 50, the function has certain quadratic form. Between 50 to 70, it has some other quadratic form and some other quadratic form. So this is quadratic functions. So this is how f of SOC will look like. Not exactly this shape. I'm not trying to say that. I'm just saying it will be like a piecewise function for three different states of three ranges of states of charge. And you can integrate over time, such that depending on the state of charge, you plug in the appropriate function f equation, and then you can calculate the Q calendar. Now, this is the calendar degradation, and here you can also see the value of f that is already calculated for different state of charges. And you can see that as state of charge is generally higher, the value of f, which is the pre-exponential factor, that is also higher. So all you need to do is, like, for given ranges of state of charge. So if your battery state of charge while trying to calculate the Q calendar is, let's say, 30%, then that means it is in this range. Then you just need to use this value of f. You can also interpolate between them. So between 20 and 30, you can interpolate between these two values. Now the idea is that all of these values of f, f is like a empirical parameter. It depends on the battery type. It depends on probably environmental conditions. It depends on various other factors. Now imagine Tesla makes a battery, or BYD makes a battery. There are many other electric car companies. They all have different battery models. So it's impossible for us to have a very nice empirical model for every single battery types. Then you will have to identify what is f for each of these batteries. Maybe the entire piecewise function like this will not look like this for different battery. This is for one particular battery type. But what is really possible to do is, irrespective of what battery an electric vehicle is using, you can definitely estimate a state of health which is dependent on the maximum battery capacity compared to its original capacity. So if original capacity was this much watt hours, then basically energy storage capacity, then after a certain point of time, at any given point of time, you can kind of estimate the capacity experimentally. So for any battery model, you can create curves like this, which plots state of health as a function of time. So this is real experimental data. So if the question is, if you have this data, can you predict the future state of health of battery, or can you model the state of health of battery? Of course you can. If you have a lot of this data, you can model to a certain extent, because there are machine learning models. You could use regression, you could use any other traditional ML methods where this data is fed into a black box and then it spits out a particular value as the state of health. That will be the output. But the real question is, can we do the same thing without using a black box model. Because if we are using a black box machine learning model where, the input is time and there is a black box BB model, and then the output is state of health. Instead of doing this, because when we do this, we are throwing all of this knowledge into the basket. We are not using the knowledge about state of charge or how the calendar degradation occurs over time. We are not taking any of that into account. Can we still create a much more accurate model which can represent pretty much any battery types, where we make use of the dynamics of battery degradation, something like this for Q calendar, plus we also incorporate some machine learning, basically neural network. So this was the idea behind implementing a scientific machine learning framework, SciML, where we take into account the battery degradation physics, whatever we know, plus a neural network framework. So this is what we will be using in this particular SciML framework for forecasting or predicting battery degradation. I did not mention about cycle degradation yet. So cycle degradation happens over multiple usages, right? So this is the equation for that. And as soon as you see this, you will see bunch of empirical parameters, A, B, C, then there is D, E, IB is the current value, and it's integrated over time. And Q is the capacity, battery capacity, as you can see here. So these empirical parameters are again estimated experimentally for each different battery types. This equation was borrowed from a paper where they performed a certain experiment on, I think it was a Nissan electric vehicle battery. So they calculated the empirical coefficients, but these values can change completely depending on the battery type. But still, the overall, this general formulation for how the rate of calendar degradation or rate of cycle degradation happens might follow similar physics. Now the question is, if we don't know A, if we don't know B, C, D, or E, but let's say we know that the cycle degradation is proportional to the current, or it's inversely it's proportional to the exponent of the temperature with a prefactor. Can this knowledge be used in devising a better model for predicting the battery's state of health? So that was the question. So now let's have a look at. I don't want to go into the details of this IB. So kind of dissecting this entire paper is not my goal in this video. The goal is more to show you how we formulated this framework, which could really make much better predictions, right? So that is what I mostly want to show you. So ultimately, the cumulative degradation is basically calendar degradation, cycle degradation plus calendar degradation. So Q total is the total capacity degradation. And state of health is nothing but 100 minus Q total. So 100 means initially the state of health will be under 100%. The fresh battery, which has not been used, which has not degraded over time, it has 100%. And then if you subtract the Q total, which is the total capacity that has been degraded, you get the state of health. Very simple. Now, what we did is we calculated the state of health numerically by calculating Q cycle and Q calendar for using these equations for these empirical parameters. Now, you might be wondering, I was saying these empirical parameters are very difficult to estimate. So why am I going back to that equation to calculate the state of health or to produce a graph like this? Why are we doing that? The reason why we did that was we wanted some ground truth data, and we can get ground truth data in three ways. One is analytical solution. So if there is a very good analytical formulation for predicting the state of health of battery, we can use that. The other, so this is basically a theoretical model. The other one is numerical solution. We can numerically solve a set of equations and calculate the state of health over time. We could have modeling like Abacus or COMSOL or something like that. We could use those models. And of course, the most important one is the actual experimental data. So we can use any of this as the ground truth to show that our framework is essentially effective, but obviously showing that our framework actually works on real experimental data for making good predictions has the highest value, obviously. But since experimental data is very difficult to obtain for a certain battery type, initially we resorted to numerical solutions. So we numerically solved the equations above for Q calendar and Q cycle, and then we calculated the Q total. Then we calculated the state of health by subtracting that from 100, and that is what we plotted here. Now, another thing which we wanted to do was, in reality, we won't get such a smooth plot. We will almost always have noise. So we added something called as Gaussian noise. So that noise will be like added on top of this like this. So that is why this plot was converted into this. So this is basically the ground truth. Now, and this is numerical ground truth, and this is actual experimental ground truth, this plot. And you can see that the experimental, it looks kind of smooth, but there are places where there are rugged edges, like it looks corrugated. And this is because of the issues that the people who performed the experiments faced. So sometimes the sensor that was supposed to measure current, it was not working. So at some point, the state of health was going to 0%. At some point, the state of health was jumping to 100%. So we had to pre-process the data a little bit after obtaining the raw experimental data to even get something as clean looking as this. But we will be using both the not without noise numerical data, with noise numerical data, and real experimental data. So first, synthetic ground truth data, right? So that is the numerical one. So we have something called as universal differential equation. So universal differential equation is nothing but we have the differential equation which governs the rate of change of Q total, right? So Q total was Q calendar plus Q cycle, and dq by dt would be, sorry for my handwriting, it's dq calendar by dt plus dq cycle by dt, right? So now we know Q calendar and Q cycle from the above equations, these two equations. So this was Q cycle and this was Q calendar, and we can calculate derivative of this pretty easy, and then we get the sum of the rate of change of rate of calendar degradation and rate of cycle degradation. Then some parameters, you can see something called NN1 and NN2 here. It's nothing but neural network. So we are replacing certain terms by a neural network here. So here you can see that this is f of SOC S state of charge by 2 multiplied by something multiplied by exponent. So you can already see that this term comes from the d by dt of calendar degradation, this one. So when we do d by dt of this, we get f of SOC by 2 times 1 by square root of t times exponent of something, right? So what we did was we assumed that we don't know whether calendar degradation goes proportional to 1 by square root of t or not. So we replace that with a neural network, because this is often the term that really governs the dynamics of any phenomenon. So for example, volume of a sphere, it's 4 by 3 pi r cube. But let's say the object shape is like random. Then we can how do we say the volume of that object scales as, not the exact volume, but just the scaling. Then we say the overall size of the object is x and the volume scales as x cube. So it's very important to know it does not scale as x square or x raised to 4 or x raised to 5. It scales as x cube. Similarly, here there is a lot of value in knowing that dq calendar by dt scales as t raised to minus 1 by 2 or 1 by square root of t. But in case we did not know the dynamics because we did not perform the experiments, let's say, we can say that is replaced by a neural network. In the cycle degradation, we are replacing the entire time by a neural network. We initially also tried experiments where each of these terms, like A, B, C, D, E, these are all empirical terms. We tried experiments where these individual empirical terms were replaced by individual neural networks. So for example, this was NN1, B was NN2, NN3, etc. That we tried, but it was way more complicated. So we replaced the whole thing by one single neural network. That is what we did. Now you will be wondering, what exactly do we mean by replacing by neural network? What is this? How do you replace a number by a neural network? So whenever I say replace by a neural network, what I mean is, if you have a quantity, you replace that because that quantity will have certain value, right? You replace whatever value that quantity has with the output a neural network provides. The output of a neural network is also a number. So you basically, whenever you say a term is replaced by a neural network, you imagine the output of the neural network replacing the value of that term, right? So here we have two neural networks, but we also have certain other terms. So this is called as a universal differential equation, because it's a combination of differential equation plus neural networks. We have one more thing called neural ODE. It's nothing but the total degradation is represented as one single neural network. The total rate of degradation is represented as one single neural network. So this f of h comma t comma theta, let's not go into the details of what is h, t and theta, but basically you just understand that here dq total by dt was not represented by one single neural network. There were two neural networks. There was some other parameters also involved, but here dq total by dt is replaced by one single neural network. Now you can imagine what would be more accurate. Can you think and predict whether it will be neural ODE or whether it will be UDE? So neural ODE is this guy, where you just have a neural network replacing the whole thing, whereas in UDE you have the little bit of physics also inbuilt, plus you replace terms that are difficult to estimate or terms that may be unknown with a neural network. And so UDE is actually more powerful because it is not completely throwing all the knowledge about the basic physics into the basket, but neural ODE is throwing everything. You're bringing everything under the umbrella of neural network. Now, what we try to do is we try to predict dq total by dt, and if we know the dq total by dt at any point of time, we can also know the state of health, because we can integrate dq. So dq total by dt, if integrated over dq total by dt, if integrated over time from 0 to t, it basically gives q total. I would say small letter q, and then state of health of at any given point of time is nothing but 100 minus this q. So this state of health, if we calculated the q total, dq total by dt using the UDE approach or neural ODE approach, then the state of health that we get will be a predicted state of health. It will be S of h predicted. But we also know actual ground truth state of health. How do we know that? We know that from these plots. This is the actual ground truth state of health. This is the numerical state of health with numerically calculated state of health with error. With noise. And this is the numerically calculated state of health without noise. And this is the actual experimental state of health. So we know the real ground truth data, and we also know the predicted state of health. Now what can we do? We can compare the predicted state of health with actual state of health, and depending on the degree of difference between predicted value and actual value, you can define an error or loss. So this loss should be minimized. So your entire goal in setting up this neural network scientific machine learning framework is to reduce that loss. So that is what we did in all of our experiments. And of course, we did a lot of hyperparameter tuning. We tried several different optimizers, several different step size. I don't want to go into the details of this because I don't want to make this lecture into a machine learning lecture. But it's more like I just want to show you that the framework involves pretty much the same hyperparameter tuning that you will do in a regular conventional machine learning problem statement, because you'll be trying. So here we tried for different time spans. So 0 to t. So t went from 1 year to all the way to 10 years, 3650. We tried different optimizers, Adam, Sophia, Ada, Belief, etc. We tried step size was pretty much the same. We realized that this was the best step size, and we also ran for many number of iterations. And you can see that we got a certain. So we are not interested in just 1 year, because 1 year is too less to make the battery degrade. We should do at least for five to 10 years. So here for a larger period of time, and this is just 2 years. So although here the loss looks like it's small for this, the loss is small in these three examples, the time for which we did the simulation also was small. So we took this one as the best set of hyperparameters because the loss was minimum and we were simulating for a good amount of time, like 7 years or something like that. So this was, I don't know if you can see this. Let me zoom in. So in this plot, it's a little bit pixelated, but basically the ground truth data is this blue color guy with the corrugated edges, and the prediction is that smooth line. And this prediction was obtained from the scientific machine learning framework using UDE. And this is over a 6-year time span, right? So, and not 7 years. So previously I said 7 year, it's over a 6-year time span. And one more thing is, if you remember, here the neural network 1, this NN1 was actually the replacement for the term 1 by square root of t. So we can compare the actual value of 1 by square root of t with whatever the neural network 1 is giving as the output. So, and if we plot that, we can see that the neural network 1 can very, very well estimate the term 1 by square root of t. So what this is showing is that the dynamics which depends inversely on the square root of time is very nicely captured by neural network 1, as you can see where this red plot and blue plot are overlapping with each other. So this is also a very, very good result. Then we had let's skip this part. Yeah, so this was about the neural ODE. So neural ODE prediction over 7 years. You can see that the neural ODE prediction of the ground truth data is not as good as the UDE. And it's understandable. It's because neural ODE is replacing the whole thing with a neural network, unlike the UDE. Now let's look at the experimental data a little bit. So here is the experimental data, and this blue color curve is the experimental data, and green is the UDE. And here you can see that the loss is small for UDE compared to the loss for loss in the neural ODE. So loss is 2.49 here, loss is 1.69 here, and you should know that this is a logarithmic thing. So the actual difference is not 2.49 minus 1.69. What this means is this is significantly better than this guy. So neural ODE, and you can also see that in the plot, like in the neural ODE, the green plot is not overlapping as good with the blue plot. Blue is experimental. This is experimental, as you can see in the legends. So my pen is having some issue. So this is, okay, I'm not sure what's the issue. Maybe I should save or something. This is experimental and this is prediction, right? So experimental and prediction are very different from each other. On the other hand, for UDE, this is experimental. Experimental is the same, by the way. It's the same ground truth. I'm not sure why am I not able to write. But anyways, the ground truth is fairly well matched by the UDE. And these are the optimizers. And for various optimizers, these are the losses that we obtained for UDE and neural ODE. In both cases, Adam was performing really well. Next is a very interesting and important thing is forecasting. So far what we saw is the ability for the neural network to learn or UDE and neural ODE to learn for a given set of data. Now the question is, given that data, can it forecast ahead? So forecasting is almost like testing. This was more like training because you are trying to fit the prediction with ground truth. It's like training, right? You know the value that you are supposed to predict, and you are checking if the prediction is matching the value that you are supposed to predict. Forecasting is more like you have no idea what you are supposed to predict, but you are trying to predict. So here what we did was over the total period of time in the experimental data, we used around 80% for training. Remaining we used for forecasting. Here, this is what you see here. So now when we do the forecast, I just want to show you how good the forecast is. 20%. So this is neural ODE's forecast, and the previous one was the UDE forecast. I should probably save this file 1 second. It's lagging maybe because my pen has made a lot of strokes. So as we expected, UDE performed much better. It has a mean squared error of 9.90, whereas neural ODE reached mean square error of 11.55 for the forecast part, because we know the ground truth data for the forecast also. So when we compare the ground truth data with what it forecasted for neural ODE and UDE, we can know that we can calculate the mean squared error. So this was the version of the paper that we published currently. Of course, we are doing more comprehensive work on by considering a few more things, which soon we'll be publishing as a follow-up paper. But this is exactly how you can introduce scientific machine learning framework into making better predictions than what a theoretical model or experimental, like a computational model, can do. Scientific machine learning really integrates the basic physics into the let's say analytic framework, or into numerical the basic physics or the numerical framework or analytic framework can be directly connected to machine learning framework. So you retain a lot of physics, but you make the model better by incorporating neural network into that. So that's it for today's lecture. If you have any questions, feel free to reach out to me, or if you would like to work on scientific machine learning related projects also, then also you can reach out. If you have any ideas for novel, interesting research problems that has real world significance, we'll be more than happy to brainstorm with you. So thank you so much, and see you again in a new lecture.